Sorry that I'm not at school today. I'm in Texas visiting my family, but I thought that I could still deliver a lesson to you through a video. Today we are starting our next chapter, Chapter 2, which is all about quadratic functions. In this chapter, we're going to explore different forms of the quadratic function. For instance, today we're going to see vertex form. Next week, we'll see standard form and factored form. We'll be learning how to graph different quadratic functions and find different features, as well as analyzing graphs that were given or maybe solving word or application problems. Today's focus is just on the first section of Chapter 2, 2.1, which is all about vertex form. So on your guided notes, you should see up at the top a spot for us to fill in what vertex form is. So I'm going to fill it in, and then we're going to come in together and talk about what each piece means. Now, a lot of what I fill in should look pretty similar because we actually saw most of this stuff last chapter, and we also saw it back in Algebra 1. So here's vertex form for a quadratic. Y equals, or maybe f of x equals, a times x minus h squared plus k. So things that maybe we remember from last chapter is that if I asked you to find the vertex, well, you could find the vertex because the vertex is based on transformations from the parent function. So if I'm translating horizontally h and vertically k, my vertex must be at the point hk. That's why this is called vertex form, is because this form highlights where the vertex is. We also know that the vertical dilation is a, and then some other things that I think are nice for us to keep in mind. If a is greater than 0, meaning it's positive, that means that my parabola opens up, or the orientation is upward. And if it opens upward, that means that the vertex is a minimum. Right? We call this the relative minimum because it looks like a valley. It is also the minimum point of this parabola. If a is negative, meaning it's less than 0, I know that that means there was a reflection over the x-axis, so my parabola has to open down. And if my parabola opens down, well, now the vertex is the relative maximum. So anytime we look at vertex form, we should know quite a few things about the function itself. We should know right away where the vertex is located, and we should also know if the parabola is oriented up, meaning it opens up, or oriented down, meaning it opens down. One last thing that's maybe helpful for us to talk about that we saw again in Chapter 1 was the axis of symmetry. So remember, the axis of symmetry is the line that cuts the parabola in half. It should always go right through the vertex. So it's always going to be the vertical line, x equals h. All right, so now that we've talked about this first vertex form, we're going to try to do a couple example problems. So the first example problem that we see is just kind of a basic graphing problem. Now, even though this function is written in vertex form, it also looks pretty similar to the functions that we saw back in Chapter 1. So maybe I start filling in the key features over here on the right because I know what the vertex is. This graph was translated, we can make a little note. This graph was translated to the right 4, and it was translated down 1. So I know that my vertex is the coordinate point for -1. So let's go ahead and graph that on our parabola. I'll go right 4, I'll go down 1. There's my new vertex. Because there's no a value, a is 1, meaning there is no dilation. So my graph should look exactly the same as the parent function. And because it's positive, I know that that means this parabola should open up. I like to graph based on the spacings of points. So from the vertex, I'm supposed to go over 1, up 1, and then over 1, up 3. If I had more space, I could go over 1, up 5, but I think that gives me an idea of what the right side looks like. And now I go do the left side, over 1, up 1, over 1, up 3. We like to see at least 5 points on a parabola, and now I could sketch it in. So let's go fill in the rest of our key features. The orientation of the parabola is up. If you want to give yourself a reason why, you could just say, because A is 1, it's positive, so that's what makes the graph open up. The axis of symmetry is x equals 4. My domain, well, the domain of any quadratic should always be all real numbers, so that one's pretty easy to fill out. My range, well, the range for this function, because it was called g of x, I'm going to use g of x for my y's. And when I go look on the graph, the lowest point that this graph ever hits on the y's is -1, which makes sense because remember the vertex was at a y value of -1, and because the parabola opened up, that meant that the vertex was the minimum value. So the lowest y value my graph ever hits is -1, and then because it continues to go upward, I know it's going to go up to infinity. The interval where g of x is increasing, well, we know that increasing means a positive slope. So looking on this graph, I could see pretty easily that this graph has a positive slope as long as I'm on the right side of this axis of symmetry. On the right side of this graph, I have a positive slope. On the left side, I have a negative slope. So my interval should go from 4 to infinity. My interval where my function is less than 0, well, I want to go look on the graph and see where it's below the x-axis. So I can tell where my x-intercepts are because they graphed really nicely. So as long as I pick x's between 3 and 5, when I look on this graph, it should have negative y's. So hopefully that felt like a nice review problem. Even though we wrote this equation in vertex form, we could have done all of this in topic 1. So let's move on and try example 2. So example 2 has us writing equations for the parabolas in vertex form. So let's start with graph A. If we're writing in vertex form, just kind of remind yourself, vertex form might have a vertical dilation, it might be horizontally translated, and it might be vertically translated. Notice that in vertex form, we do not have any horizontal dilation. That does not show up in vertex form. So first thing I like to do is identify the vertex. So here's the vertex up at the top. I'm going to make a little note. It's at the coordinate point -1, 8. So I know that when I'm filling this thing in, I can go ahead and write x plus 1 squared plus 8. If I want to figure out what my vertical dilation is, that's where I go back and I look at the spacings of the points. The first thing I see is that because this parabola is downward facing, I know that A had to be negative. When I go look at how I go from one point to the next nice point, it looks like I had to go over 1, down 2, and then over 1, and then down 6. So that tells me that my vertical dilation must have been by a factor of 2 because I took what was my original vertical of 3 and of 1 and I multiplied it by a dilation of 2. So that means A must be -2. So now I've written the equation of my parabola that has a vertex at -1, 8 and a vertical dilation of 2, and it's been reflected over the x-axis. All right, next one. I want you to pause the video, and I'm going to give you a second to try it. So Mr. Rude, pause the video and give students a couple of minutes to try the problem. All right, hopefully you tried this problem. Let's check it together. My vertex is down at the point 2, -3, so I'm going to make a little note of that. So right away, I should be able to fill in. I was translated right 2. I was translated down 3. In order for me to find the dilation, I'm going to go look at my points and see how I get to the next one. So it looks like this is the next nice point on my graph. And to get there, I had to go over 1, and I went up 3. Well, the normal spacing is supposed to be over 1, up 1, so that means that my vertical dilation must have been 3. It's +3 because this parabola opened upward. All right, let's move on to part C. This is also one that I'm going to have you try, although I think it's maybe a little bit trickier. So Mr. Rude, will you go ahead and pause the video to give students a chance to try Part C? All right, hopefully you had a chance to try it. So I'm going to go look where the vertex is. So I see the vertex at -3, 0. So I can go ahead and fill in again. I was translated right 3. I was translated, oops, and I kind of need to leave space there. Let me make sure I have room for my vertical dilation, if there is one. And you could put +0 at the end if you want. You don't really need to, because when we add 0, it does nothing. So to find my dilation, what I notice is when I go over 1, it looks like I only went up a half. And then I went over 1, and this time I went up 1.5. And then over 1, and now up 2.5. So each time my distance, think about what the distance was supposed to be. This first distance was supposed to be 1, but it's a half. This second distance was supposed to be 3, but now it's 1.5. This final distance was supposed to be 5, but now it's 2.5. So all of my original distances were multiplied by a factor of a half, so my vertical dilation is a half. All right, let's move on to our next set of problems. So flip over to the back. So up at the top, we have two problems where we're going to try to write the equation of a parabola given the following features. This problem is pretty similar to the one that we just saw, except we're not given the graph. So I'm still going to rely on my vertex form, which I like to rewrite just to remind myself of all the things that I want to plug in. Because I was given the vertex, the first thing I'm going to do is plug the vertex in for h and for k. I was not told anything about this dilation, so for now, I'm just going to leave my dilation as a. Now that I've plugged in my vertex, I go look at the second part of the question, which has the information that this parabola passes through the point 1, 1. If it passes through the point 1, 1, that means I should be able to plug in 1 for y, because that was the y coordinate. I should be able to plug in 1 for x, because that was the x coordinate. And this is going to allow me to find a. So if you're ever in a situation where you're given the vertex and you're asked to come up with the equation, you have to be given some other coordinate point that you can plug in and find a. So now we just get to simplify. So let's see, 1 minus 2 is -1. If I subtract 3 from both sides, I'll go ahead and do that. When I subtract 3 from both sides, I get -2. I know that -1 squared is just 1, so it looks like a was -2. Now once you've found a, you should go ahead and write your final equation. -2 times, we already knew where the vertex was, so now we're just filling that part in. All right, so now I'm going to give you a chance to try part B. So part B is very similar. The vertex is at the point 1, 0. The y-intercept is the point that you are given. So I would start by plugging in my vertex, and then I would use that y-intercept to find a. So again, Mr. Rude, if you would pause the video and give students a couple of minutes to try this problem. All right, so hopefully you had a chance to try it. Let's just go over it together. So again, I'm going to go fill in. My vertex was at 1, 0. Just like the problem we saw a minute ago, you don't have to put +0. I like to do it to remind myself that that's the y-coordinate of the vertex, but you don't have to put it if you don't want to. I'm going to go take my coordinate point, that y is 4 when x is 0, and now I just get to simplify. Well, -1 squared is just 1, so again, it looks like a was 4. So now I found a, I'm ready to write my final equation. I already knew where the vertex was, and again, you could put +0 or not. All right, so hopefully we're feeling pretty good about writing equations, whether it's from a graph, whether it's from some pieces of information. So let's move on